In the next section of this chapter on unit commitment, we'll be studying Lagrangian relaxation. Lagrangian relaxation is a computational technique for approximately solving problems such as the unit commitment problem. The idea is that we take the dual of the system constraints and then we maximize the dual. So our original primal unit commitment problem, required us to minimize over zk's and xk's the objective subject to the equality constraints ax equals b, cx less than or equal to d. We dualize those constraints, which is to say we bring them into the objective by multiplying them on the left by suitable dual variables lambda and mu, and then we try to find the maximum over lambda and mu greater than or equal to 0. Lambda corresponds to the Lagrange multipliers on the equality constraints, mu corresponds to the Lagrange multipliers on the inequality constraints and is required to be non-negative. We maximize over lambda and over non-negative mu this minimum of the over z and x of the Lagrangian. This is analogous to solving the economic dispatch problem by dualizing the system constraints. And we're going to consider the use of a similar pricing rule to that used in offer-based economic dispatch. But instead of being based on the Lagrange multipliers, it's going to be based on either the current value of the dual variables at a particular iteration of maximizing the dual, or indeed if we can find the maximizer of the dual based on the maximizer lambda star and mu star of the dual. When we dualize, we separate the unit commitment problem into a subproblem for each generator that involves profit maximization, or a problem equivalent to profit maximization for the generator given the value of the dual variables, and the problem of finding the values of the dual variables that maximize the dual. We can think of each generator as maximizing its operating profit for the given vector of prices as specified by the current value of the dual variables. And then we could in principle update the dual variables until a maximum is found. Typically there is a duality gap. That is to say, the maximum of the dual is strictly less than the minimum of the original primal unit commitment problem. And indeed, in the case when the duality gap is non-zero, we typically find that the information that we get out of Lagrangian relaxation doesn't yield a feasible solution to our original unit commitment problem. So typically we need some sort of ad hoc post-processing step to produce a solution that satisfies the system constraints. Such ad hoc steps are somewhat problematic in a market context because they're typically partially understood by the market participants and then present opportunities for market participants to influence the outcomes through changes to offers that don't really represent economic fundamentals. And in practice, although North American ISOs used to use Lagrangian relaxation, all of them now use or are moving towards using mixed integer programming software to solve unit commitment problems. Nevertheless, there are some very helpful insights that come from the maximizer of the dual, and we can find those insights to be helpful even in the case where we don't get the optimal unit commitment solution out of the dual. Let me give an example. We already met this example actually in section 4.8.3 in the context of discussing duality gaps. We had a single generator and we wanted it to meet a demand of D overline equals 3 megawatts. We had a single period model, so this isn't going to illustrate all of the complexities of startups, but it will capture nevertheless some of the issues associated with duality gaps. The generator had two variables associated with its operation, the unit commitment variable, Z, and the production variable, X. X was simply the production of the generator. And our cost function was of the form f of Zx is equal to 4Z plus X. In other words, if the generator was committed, we incurred a cost 4 times 1. 1 corresponds to the generator being committed, and then if it were generating anything it would be incurring an additional cost x, in other words, proportional to the generation. Moreover, we had a constraint that required x to be between 2z and 4z. In other words, when the generator was in service, it had to produce between 2 and 4. So if the generator were paid lambda for its production, then its profit maximizing behavior would be do nothing if lambda was below 2, either produce nothing or produce 4 if lambda is equal to 2, and to produce 4 if lambda were greater than 2. In other words, no price would equate supply to demand of 3 megawatts. So if we generalize that a little bit, let's consider a generator with cost function 4z plus beta z, where again z is the commitment variable, x is the generation. We'll keep its production between 2 and 4 when it's in service, but now we'll consider the possibility of beta taking on different values. Let's again suppose that the generator is paid lambda for its power production x, and then it finds the value of production that maximizes its profit. We did a very similar analysis to previously, so I'm going to move fairly quickly over it. If we want to maximize the profits, which is lambda times x minus f of zx, and that's equal to lambda minus beta x minus 4z, we need to compare the profit when we're out of service, which is a profit of 0, to the maximum profit when it was generating between 2 and 4 if z is equal to 1. And we consider various cases. For example, if lambda is less than or equal to beta, then we find that profit maximization occurs when we stay out of service. Profit would be 0 in that case. That's not such a good profit, but it's better than we could do if we were in service. If lambda is between beta and 1 plus beta, we find again that profit is maximized by being out of service. If lambda is exactly equal to 1 plus beta, then we find that for x equals 4, the profit would be exactly equal to 0 if we were in service. If x were less than 4 but greater than or equal to 2, the profit would be negative. So for this particular value of lambda, the profit function has two maximizers, either out of service and producing nothing, or in service and producing 4. And if lambda is greater than 1 plus beta, then a similar argument to before shows that profit maximization occurs when we're in service and generating at 4 units. So if the generator were paid lambda for its production, then its profit maximizing behavior would be don't generate anything if lambda is less than 1 plus beta, generate either 0 or 4 if lambda is equal to 1 plus beta, and generate 4 if lambda is greater than 1 plus beta. If we had just one generator and it had marginal cost beta, then there will still typically be no price that equates supply to demand, unless the demand happened to be equal to 0, not very interesting, or 4. The price 1 plus beta at which the generator starts to produce, of course, depends on beta. So we'll still typically have a duality gap, since the minimum of problem 10.1 will be strictly greater than the maximum of problem 10.2, the dual problem. But the reason for introducing this variable beta was to consider a larger example when we had a collection of generators that was slightly different. So let's suppose we generalize the example that we just met to the case where there are multiple generators with different cost characteristics and a larger demand. So in particular, let's suppose that the demand was 303 megawatts. As previously, let's ignore reserve requirements, although that doesn't change the fundamentals of our situation very much. Again, that is to say, xk is equal to pk, the generation by generator k. Let's suppose there are 100 generators, and generator k has cost function fk of zk xk that's given by 4 times zk plus beta k xk, where for each k, beta k is 1 plus k on 100. So we're going to have a collection of 100 slightly different generators. Feasible operating set for each generator is exactly the same as the feasible operating set for our previous single generator example. So, since each generator has a slightly different operating cost function, higher values of K are associated with more expensive generators, we can, by inspection, observe what the solution of the optimal unit commitment problem is. The lower values of K correspond to lower cost generators, and so in order to meet the demand of 303, we would like to commit generators 1 through 75 and operate them at full capacity. We want to commit generator 76 to produce 3, and generators 77 through 100 should be off. In this case, we can calculate the minimum cost. It's the sum of K of 1 through 75 of the cost of each of generators 1 through 75 to operate at 4 units. The generator has to be in service, Zk has to be 1, and Xk has to be 4. Moreover, generator 76 has to be in service and operating at 3. That comes to a total of 723.28 and is the minimum of problem 10.1. In general, unit commitment problems, particularly when we have realistic cases with more than one interval and transmission constraints, are a whole lot more complicated than this. But in the case of this very simple problem, we can just, by inspection, figure out the problem. We're also going to consider the maximizer of the dual problem, and we'll see how it provides insights into the minimum and minimizer of problem 10.1. And let me emphasize that these insights can be helpful from an economic intuition perspective, even if we can't find the minimum and minimizer of problem 10.1. So the dual problem, problem 10.2, is the maximum over lambda. We don't have any system inequality constraints, and we just have the single power balance constraint that the sum of the generations should equal D overline. So we'll dualize that constraint, and we'll find the maximum over lambda of the minimum of the objective plus this value. Remember, however, that because F separates and because these terms separate, we can think of these as a collection of profit maximization problems. And in particular, what we find is if lambda is between 2 plus 75 on 100 and 2 plus 76 on 100, for example, to be concrete, let's suppose lambda is 2.755, then this is just big enough such that generators 1 through 75 will each produce 4 megawatts because it's just above 1 plus beta k for each of k equals 1 through 75. On the other hand, it's below 1 plus beta k for k equals 76 through 100, and consequently the total production will be 300 megawatts. The dual function in this case, adding it up, adds up to 722.265. That's just a little bit less than the solution of the unit commitment problem. Furthermore, if we had a lower price, what would happen would be we would commit less generators, and in fact you can check that the value of the dual would be less than or equal to this value. On the other hand, if we push the lambda a little bit larger, let's make it a little bit bigger than 2.76, for example, lambda equals 2.765, then we'd find that generators 1 through 76 would produce 4 megawatts, 77 through 100 would produce nothing. Total production in this case would be 304 megawatts. This is more than we wanted. The previous case was less than we wanted. And the dual function in this case would be 722.275. And again, you can check that if lambda is bigger than 2.77, we'd find that the value of the dual would be less than or equal to 722.275. One more observation: if we let dual equal 2.76, we'd find that that would actually correspond to the maximizer of the dual. So let me write lambda star is equal to 2.76. What we would find is generators 1 through 75 would produce 4 megawatts, generators 77 through 100 would produce nothing, and generator 76 in this case would be indifferent to either not producing, that is to say producing 0 megawatts, or producing 4 megawatts. These two cases would correspond to total production being either 300 or 304, and in this case the dual function, whether we consider the case where the generator 76 is not generating or is generating, we'd find that in both cases the dual would be 722.28, and that is indeed the maximum of the dual. Well, putting all those previous slides together, there's still no price where supply equals demand. Remember, demand was 303 megawatts. However, the supply-demand constraint, if we think of the violation, the relative violation, notice that the violation is relatively much smaller than in the smaller example. In particular, we're only violating it by 3 or 1 megawatts. By judicious choice, it would be only violated by 1 megawatt in this case out of 303, whereas previously the violation was by, let's say, a megawatt out of 4, a much greater relative violation for the small example. Furthermore, the commitment and dispatch decisions are pretty close for almost all of the generators. For generators 1 through 75, the commitment and dispatch decision is to be committed and to operate at 4. For generators 77 through 100, the commitment decisions are to be off, not producing anything. So the only generator that we didn't get right was generator 76, given the price lambda star equal 2.76. The duality gap is 723.28 minus 722.28, which is only 1 unit. So the duality gap is relatively smaller as a fraction of the minimum of the unit commitment problem, just as the violation is relatively smaller. So in both the first example and the larger example, there is a duality gap. The maximum of the dual, obtained by dualizing the system constraints, is strictly less than the minimum of the primal problem. The commitment variables and the dispatch variables do not satisfy the system constraints. However, having said that, the duality gap is relatively smaller in the larger example, and the system constraints are violated by a relatively smaller amount. So the commitment and dispatch values can provide, in fact, we could just modify the dispatch of generator 76 in order to figure out the optimum of the unit commitment problem. In general, it's not quite as easy as in this example. If the generator cost characteristics are heterogeneous, however, then the duality gap and the violation of the system constraints becomes relatively smaller as the number of generators grows large. And this is indeed the key to application of Lagrangian relaxation to large-scale systems, since the post-processing step involves a smaller adjustment. You might think about the reasons why generators might either be homogeneous or heterogeneous in a market. Unfortunately, the non-zero duality gap tells us that the prices on the system constraints alone cannot result in profit maximizing generators committing in a dispatching in a way that's exactly consistent with optimal commitment and dispatch. No matter what price we pick, some system constraint will fail to be satisfied by the resulting profit maximizing decisions of the generators. Steve Stoft argues, however, that if we modify the demand slightly, we could obtain a dispatch supporting prices. So if the generation stock is heterogeneous, then the modification will be small. In the larger example, actually in the smaller example as well, the modification would be at most 2 megawatts, and in the larger example, that would be a relatively small change to the demand. Since there are other uncertainties and errors in the dispatch, it may be reasonable to ignore the duality gap in this case. And indeed, this is the basis of a principled argument against centralized unit commitment as performed by ISOs. However, for the remainder of our development, we'll continue to assume that the ISO performs centralized unit commitment. ERCOT and other ISOs optimize the commitment and the dispatch in the day-ahead market, reflecting the complexity of the various constraints, particularly transmission constraints. In the next section, we'll develop an approach to inducing the generators to produce consistently with optimal commitment and dispatch as determined by the ISO. We'll see that it involves an additional make-whole payment to some generators. So, as we just discussed, the non-zero duality gap means that prices on system constraints alone cannot encourage profit-maximizing generators to all commit and dispatch consistently with optimal unit commitment. However, in our larger example, all but one of the generators would be committed and dispatched correctly if the price were equal to 2.76. As we said before, generators 1 through 75 would produce 4 megawatts. Generators 77 through 100 would produce nothing, and that is exactly what they're supposed to do, or is exactly consistent, I should say, with the optimal unit commitment and dispatch solution. And they would collectively produce 300 megawatts. We then need to ask generator 76 to produce the other 3 megawatts in order to meet the demand of D-overline. What would it cost generator 76 to do this? Well, just plugging in its cost function, we'd find that in order to generate 3 and be committed, it would cost 4 times 1 plus beta k, which is 1 plus 76 on 100 times 3, which is 9.28. For our energy price of 2.76, for 3 megawatts, generator 76 would receive 8.28. So if it produced 3 units, generator 76 would lose $1 an hour. Or to put it another way, generator 76 would need an additional payment of $1 an hour in order to have a non-negative profit, in fact a zero profit, based on the energy price of $2.76 per megawatt hour. This difference, by the way, is exactly equal to the duality gap. So, this suggests an approach. Let's suppose the ISO determines prices lambda star for energy, and in general there would be reserve prices mu star using some algorithm. For example, the maximizer of the dual from Lagrangian relaxation. This leads to what is called convex hull pricing, but I should point out that most ISOs currently use a different approach for energy and reserve prices. We'll describe that in a moment, but for now the key point is that we have some prices for energy and reserves. We're going to consider the profit maximizing response to these prices, whatever these prices happen to be. For some generators, their profit maximizing generation based on these energy and reserve prices will be consistent with optimal unit commitment and dispatch. For these generators, we simply pay them based on the energy and reserve prices. That's the end of the story for those generators. However, for any generator such that their profit maximizing activity would not be consistent with the ISO calculated optimal unit commitment and dispatch, what we'll do is we will pay them an additional make-whole payment that will induce them to generate consistent with optimal unit commitment and dispatch. So, in particular, for generator 76, what would be the appropriate price? Well, as we said, we need to give them an extra $1 per hour. Let's see if we can write down a general expression for the make-whole payment. It needs to induce the behavior consistent with optimal unit commitment and dispatch. Let's consider energy prices and ignore reserve prices for now. So suppose the ISO specifies a vector of energy prices lambda star. In general, there'd be a different price for every hour of the day. We'll consider two cases. First, generator K can choose its commitment ZK double star and dispatch XK double star to maximize its operating profit given the price lambda star. The second case will be generator K commits and dispatches consistent with the solution of optimal commitment and dispatch, which we'll continue to write with a single star. So first, generator profit maximization. Given the price is lambda star, the profit would correspond to maximizing revenues minus costs. Given the price is lambda star, the revenues would be lambda star transpose times xk. The costs we need to subtract off that would be fk of zk xk. And maximizing that would result in the maximum profit. I'll write that as profit k double star as a function of lambda star. Different values of lambda star would result in different profits. And I'll emphasize again that the double star refers to generator profit maximization. Let's now turn to optimal commitment and dispatch from the ISO problem. Given an energy price lambda star, and given that the generator actually operated according to the optimal commitment and dispatch as determined by the ISO, not necessarily optimizing the generator profit, but providing the commitment and dispatch that's needed to meet demand, for example, generator 76 producing 3 megawatts, then the profit for generator K would be given by lambda star transpose xk star minus fk of zk star xk star. Notice that the profit maximum is at least as much as this value, right? This is a particular value of profit for a feasible solution. The profit maximum must be at least as bigger than that. Furthermore, if they're equal, then the profit maximizing decision of generator K is completely consistent with the ISO optimal commitment and dispatch. In this case, we could say that the vector of prices supports the ISO optimal commitment and dispatch, just as previously we discussed a vector of prices supporting the ISO dispatch. So let's consider our cases. If the maximum profit is equal to the profit under ISO commitment and dispatch, then the profit maximizing behavior of generator K in response to lambda star alone is consistent with optimal commitment and dispatch. We don't need any make-whole payment. On the other hand, if optimal profit is more than what the generator would have got if he followed the commitment and dispatch from the ISO, then the profit maximizing behavior of generator K in response to lambda star is inconsistent with optimal commitment and dispatch. Lambda star alone will not induce the generator to do what the ISO wants it to do. We need to rejig things so that the generator will be happy to behave according to zk star xk star. We need to pay it an additional make-whole payment that's exactly equal to the difference in profit, maximum profit, and the profit under the ISO commitment and dispatch. That will make the generator indifferent between operating according to its profit maximizing solution and operating according to the ISO desired commitment and dispatch. And we can combine both of these cases by observing that the payment is equal to the difference between the maximum profit and the profit that we would get under ISO dispatch in both cases. Let me emphasize that the make-whole payment is only made to generator K if generator K commits and dispatches according to zk star xk star. And by design, the make-whole payment would adjust the profit for generator K so that zk star xk star is consistent with generator K maximizing its profit. In principle, there's no additional inducement necessary for generator K to behave consistently with centralized optimal unit commitment and dispatch. Nevertheless, we typically need to set a tolerance on the commitment and dispatch being close enough to zk star xk star to qualify to receive a make-whole payment. And we'll see that's particularly the case when we consider a simplified make-whole payment, as I'm about to explore. So to develop a simplified make-whole payment, let's notice that there are really three possibilities for profit maximizing behavior: ZK double star, PK double star by generator K in response to the price lambda star. The first alternative is that the generator doesn't commit. In other words, ZK double star is 0 and therefore PK double star is 0. So that would mean that the profit, the operating profit, is 0, and of course that's got to be greater than or equal to the profit under the ISO desired commitment and dispatch. The second alternative is that the generator is happy to commit and dispatch consistently with optimal commitment and dispatch. In other words, ZK double star is equal to ZK star, PK double star is equal to PK star. And in that case, the profit maximizing solution is the same as the profit under the ISO commitment and dispatch. The third possibility is that the generator commits and dispatches, but that commitment and dispatch is not consistent with the ISO commitment and dispatch. That is to say, either ZK double star is not equal to ZK star, and PK double star is not equal to PK star. And of course, in that case, the profit would be the maximum profit would be strictly greater than the profit under the ISO optimal commitment and dispatch. In the first alternative, the make-whole payment would be required to make the generator indifferent between not committing and committing and dispatching consistently with ISO optimal commitment and dispatch. This term, costs minus revenues, when added to the revenues will exactly compensate the costs and make the generator indifferent between not committing and therefore getting no payment and committing and dispatching consistently with the ISO commitment and dispatch. In the second alternative, there's no make-whole payment required. So if we could ignore the third alternative, we could think of the make-whole payment as being the maximum of 0 and this difference between the operating costs under ISO commitment and dispatch and the revenues under ISO commitment and dispatch. In the case that this term is negative, then we don't need any further inducement, and indeed this resulting max of 0 and a negative number would be 0, no make-whole payment. If, on the other hand, the cost is bigger than the revenues, then the make-whole payment will exactly compensate this term, cost minus revenues. So that simplified make-whole payment is used in ERCOT and in other markets, even though it doesn't quite have the correct incentives, in particular in the case that the profit's not 0, the optimal profit's not 0, and the profit is bigger than the profit under ISO commitment and dispatch. So in this case, to ensure that the behavior is actually consistent with optimal unit commitment and dispatch, the make-whole payment is only paid when the generator K actually commits and dispatches close enough to the ISO solution. And as a general rule, there would be a penalty if the generator deviates too far from ZK star and XK star. So let's look at the case in the example. To achieve optimal unit commitment in the example, we'll price the energy based on the dual maximizer. That would be lambda star equal 2.76. Profit maximizing behavior of generators 1 through 75 and 77 through 100 in response to this price is completely consistent with centralized optimal unit commitment and dispatch. So we don't need to pay any of those generators any make-whole payment. However, we need to pay an additional make-whole payment. We need to pay a make-whole payment to generator 6. It needs to be equal to the profit, that should be profit double star 76 of lambda star, minus the profit in the case of being consistent with commitment and dispatch, which is equal to 1 unit. So generator 76 requires an additional $1 an hour to induce it to generate consistent with optimal commitment and dispatch. The make-whole payment would only be paid if generator 76 commits and dispatches consistently with the optimal commitment and dispatch. The demand would pay for energy based on a price of lambda star times D overline. That's 2.76 times 303, which is $836.28 an hour for energy, plus an additional make-whole payment of $1 per hour. So it ends up paying total of $837.28 per hour. The make-whole payment is charged as an uplift to demand. Notice that the prices are no longer anonymous. They depend on the generator. The payments are no longer anonymous, since the payment to generator 76 is different to the payment to other generators, since it involves a make-whole payment. Let me just observe that demand response can reduce the duality gap and therefore reduce the make-whole payment required to achieve optimality. To see this, let's suppose that instead of a fixed demand of 303 megawatts, the demand was the sum of mostly fixed demand, 290 megawatts, plus a price-responsive demand, let me call it delta D, and let's suppose it had a willingness to pay of 2.755 plus 10, in other words, $12.755 per megawatt hour minus $1 per hour times delta D. In other words, the bigger delta D is, the lower the willingness to pay. This is a sloping demand curve, and delta D is in the range from 0 to 20 megawatts. This is similar to the demand curves we've seen before. At a price of lambda star equal to 2.755, the price responsive demand would be, if we plug in and invert this equation, we'd find that delta D is 10 megawatts. Let's check that. Delta D equals 10 megawatts times 1 would give us 10. That 10 would exactly cancel this 10, resulting in $2.755 per megawatt hour, corresponding to the clearing price. So that the total demand would be 290 plus this particular value of delta D, which is 300 megawatts. Remember that at a price of 2.755, the supply actually equals 300 megawatts. So supply equals demand, and there is no duality gap and no need for a make-whole payment. In general, price-responsive demand can reduce the duality gap and reduce the make-whole payments. This demand response example is somewhat unrealistic in that demand is not generally willing to curtail, voluntarily curtail, at prices that are close to typical generation marginal costs. So we're going to assume fixed demand in subsequent examples. However, price-responsive demand definitely does have an important effect in the presence of scarcity and or market power, where offer prices might otherwise rise to far above the generation marginal costs. I'll again refer you to my market power course. And as we've already seen in section 8.12.7.7, there may be representation of responsive demand for adequacy reserve that may induce a demand curve that has similar properties to the one I've described.